The title of my talk, and the work is joined with Dr. Goncharov. It's about the Galois group, or rather the fundamental Hopf algebra of the category of mixed Hodge Tate structures. So first, our goal is let MHTS, we denote by MHTS or MHTS the category of Q mixed Hodge Tate structures over or V MHTS over X to be the variation over X. So our goal is to construct a Hopf algebra A, or rather AC, and then we will show that the fundamental Hopf algebra of the category of mixed Hodge Tate structures is equivalent to the graded comodule of AC. And then we will give some generalizations. So generalizing our construction, we can replace the C by any R, and we explain what any means. And we'll give some applications. For example, how can we explain the category of variations of mixed Hodge Tate structures? Okay, that's how we go. Now, overview for today's talk. First, I will give some brief introductions, and then we'll talk about the Hopf algebra and its relation to the category. Then we'll give the generalization, and only at the end we will give the detailed constructions of our Hopf algebra. So first, some introductions. So first, let's fix some notations. So here, everything is basically over Q. In the generalization, everything is over K. So for example, mixed Hodge structures are over Q. Tensor always means over Q. C star means C star tensor over Q, tensor by Q. Or we can also consider it as C or C1 mod out Q of 1. So it's basically a Q vector space. We usually use a capital letter for some number here, or exponential of a lowercase or lowercase of bar to denote an element here. So it means x mod 2 pi m cubed. So the last notation is the standard notation for tensor algebra. That's the notations we need. And yeah, here let me explain our notation for the period matrix of a mixed Hodge Tate structure. So we can use a period matrix to present an object here. For example, if we have this period matrix, let me briefly recall what the mixed Hodge Tate structure is. So we denote the columns, the first column, second column, third columns, by C0, 1, and 2. And we let EI to be the standard basis, 1, 0, 0, 0, 1, 0, and 0, 0, 1. We consider they all lie in the column space Cn. And the matrix corresponds to a mixed Hodge Tate structure. So VQ is the Q vector spaces spanned by the columns, and we can define weight filtration. Basically, we consider the first column as Q of 0, second column as Q1, third column as Q2. And the Hodge filtration is given by the standard basis, that is, F1 is 0, F0 is E0 only, and basically E2 gives F minus 1, E1 gives F minus 1, and E2 basically gives F2. So this is a Hodge structure, mixed Hodge structure we are going to use. So this is just an example. Okay, our story may start from the single-valued polylogarithms, for example. So first, polylogarism can be defined recursively. L1 is some log, and Ln plus 1 is the integral of Ln dt over t. Note that the path to define the Ln plus 1 must match with the path to define Ln. So there are some well-known single-valued versions of this polylogs. For example, the trivial log, we have the real part. And for dilogarithm, we have the block Magnus dilogarithm. Analyzing these results, we can observe the following single-valued functions. Well, in fact, they take values in our A, Hopf algebra A, related to the polylogarithms. For example, V2, they can correspond to this thing, exponential, basically exponential of V2, basically Z, and 2 pi here, and negative V1 here. And another example is log x tensor log y. We can associate a x tensor log y, y tensor log, so there's a type of y tensor log x. Exponential of log x log y tensor 2 pi. It still lies in C star tensor C. I should mention that we are not the first one who observed this. For example, I think the study of this is going to go on. So, one remark is one may as well recover the single-valued, real-valued function from the constructions above. For example, if you take the log of the first component in C star and then take the real part, multiply with the imaginary part of the second part, then we go back from this function, we go back to the block-Riemann algorithm. So this thing tells us we can extract a lot of information from the periods of the mixed Hodge Tate structure here. Okay. Oh, that's some brief introductions. Now we can talk about our main object, the Hopf algebra A. So to construct our Hopf algebra A, the input is, so first C as a Q algebra, and with a special subspace, the Tate structure Q1 as a subset in C. And the output is a graded commutative Hopf algebra, denoted by AC or simply A. So we will only have a preview of this Hopf algebra. We will give the definition at the very end. Before that, we may pretend we only know the weight less than or equal to 2 part. So they are, so A0, so A is the direct sum of A0, A1, A2, and A0 and A1 is C star, A2 is C star tensor C. Recall that C star is considered as a Q vector space, and this tensor is a tensor over Q, tensor as Q vector spaces. Now we want to introduce a coproduct. For example, A2 mapping to A1, A1. That is C star tensor C to C star tensor C star. That's the one you can think of. It is X tensor Y, and you just lift Y to C star. That's the basic decomputation coproduct. The product is a little bit unusual. So A1 tensor A1 going to A2, C star tensor C star to C star tensor C. So then X tensor Y goes to X log Y, Y log X. However, this one, this is basically the shuffle product. However, we say that that's not the correct product we want to use here. We need a term to modify this. This non-shuffle product. We may call it the quasi-shuffle product. Okay. In fact, till now, we already know a quotient of A, of this Hopf algebra A. A quotient by the part of weight greater than or equal to 2, or greater than 2. Okay, let's have a glance at the Hopf algebra. Now, why they are useful. So now let me state our main theorem. There is a canonical equivalence of categories. The category of mixed Hodge Tate structures is canonically equivalent to the category of graded comodules of AC. So let's recall what it means by...
What's the fiber functor?
Oh, the fiber functor, yeah. It is not here. The fiber functor is the graded associated with respect to the weight filtration. Yeah. Let's recall a little bit of Tannakian formalism. So consider the category with a fiber functor which forgets the weight filtration. With respect to the field, this is the forgetful functor to vector space. Then the Galois group is defined to be the algebraic group of tensor automorphisms of this functor. That is, this category is equivalent to the representation of this algebraic group. The algebra is this. The embedding graded vector, which is equivalent to the category of pure Hodge Tate structures, it embeds into MHTS. This gives a decomposition of this. I think Gene also mentioned similar things in his talk, where U is pluripotent. And we also have the forgetful functor. So that's the splitting. Splitting from Gn. This gives the splitting from Gn to G.
So a comment there is if you took omega to be Betty, then you have to choose an isomorphism between graded omega Betty and omega Betty to get a splitting. If you take omega to be Durham, then it's naturally isomorphic to its associated graded.
But he doesn't. You don't use a splitting.
No, we don't use this splitting. Yeah.
You don't have to choose it.
So the first part, this is the embedding from the pure Hodge Tate structures to mixed Hodge Tate structures. I think this is canonical, and I think this is also canonical. So I think no choices involved here. So okay, that says we can split this short exact sequence, and that tells us this category is equivalent to the graded comodule of all of U. That is the graded representation of U. Graded just means the action of Gn. And our theorem just says our Hopf algebra is canonically isomorphic to all of U. Here I only give a quick sketch of the proof. Our idea is to use the graded Hopf algebra of equivalence classes of framed mixed Hodge Tate structures, the framed objects in this category. Then we know there is a canonical equivalence of these two categories. And our goal is just to provide a canonical isomorphism from this Hopf algebra to our Hopf algebra. And the formula looks like this. I won't explain what it really means, but in short, it starts from a framed object and together with the splitting, and it involves some periods. Just some.
S means splitting.
S means splitting, yes.
Depends on splitting?
No, it does not depend on splitting. So as long as we go back to this space, it does not depend on splitting.
Okay, did you say what A is in every degree, or?
Yes, A is in every degree.
But did you give the definition already?
Yeah, no, not yet.
Okay.
We only give a preview up to way 2. So for now, it's a black box. Now, what is the period map P? Here I will go to the example. So P sends a split. It won't depend on the splitting. A split framed mixed Hodge Tate structure to an element in our Hopf algebra. Let me see how it works. Let's see how it works. So, for example, if we, for now we are working on the point. So fix a Z, then this matrix, as we see that stated before, defines a mixed Hodge Tate structure. And we send this to the item on the right. So how do we get this? So you can, commutatively you can go this way to get this period V2 and put it here. Or you can go this way, again, to get the periods log Z and Li1. So and put log Z here, put Li1 here. and make sure everything is of weight 1. We take the exponential or take the quotient in the first component. And we can see the right-hand side is well-defined in A. For example, the monodromy at 1 gives, it changes V1 by 2 pi I, it changes V2 by 2 pi times log Z, and we see the right-hand side is well-defined. It doesn't depend on your choice of V1 and V2. So basically that's how it goes. So once you have write down the matrix, you can easily just go upstairs to find all the terms on the right-hand side.
So you define a map from OU to your algebra A.
Yes.
Does that factor through the co-product on OU? Does it go OU, goes to OU, tends to OU, and then to A? Because this map certainly factors through the co-product, the natural co-product on OU.
I don't think it factors through the... It's compatible with the co-product structure.
So it is a map of coalgebras.
Yes, yes. It will be a map of Hopf algebra.
So it looks like this map factors through the co-product. In this example, it certainly does.
No, because I think the co-product of the left-hand side is basically this matrix tensor this matrix. So
that's the reduced part.
Oh yes, yes. Well, in that sense,
I think it looks like it does.
yes.
I think A to C looks like a co-product. It looks like a tensor. That's why it looks like.
Well, it's slightly. Maybe it is, but yeah, we have to check how it works. Yeah.
So I just have one more question. You have a sum of two terms. On the first term, the Li2 is on the left-hand side, and on the second term, the Li1 is on the right-hand side.
Yes, that's why we see we go from the lower right to the upper left. So, for example, we go here and here. So we take log Z first, and then Li1. So log Z first, and then Li1. And if you go this way, you get V2 first, and you put a 2 pi to take the place. And that's the rule of the game. So you always go from lower to higher ones. Okay, that's an example of the period map P. Okay. Okay, so I think I kind of explained the proof why there is a period map. Yes, I should mention that the period map is a map of Hopf algebra, although I didn't really introduce the complete structure, Hopf algebra structure I see.
Could you explain the notation at the bottom of the last page?
Yes. And P means the period map. This is a framed object with framing V0 and Fn. And S is a splitting, that is, we can choose any splitting now. And on the right-hand side, there are some signs, and the sums of some tensors. First, we put some signs and put some tensor products. Each part is some tensors, and the first part is a period. And we put some 2 pi i's here to take the place. And here, for example, the period on this page, for example, if you take V0 and F1, you will get V1, normalized.
What is small s in your?
It's a splitting. That is. Smaller s, in fact, it means. Could everyone see this? S means a splitting grow W V to V. I think the rational is one is enough. So there's no canonical choice of this, but we showed that the construction there does not depend on the splitting S. So till now, what I want to state is we constructed some A and showed that it is equivalent, it is isomorphic to the Hopf algebra of equivalence classes of framed objects. Yeah, that's it. And it's defined through some period maps. Okay, so why our result is interesting in some sense? Because a priori we know some description of this overview by Benedict's vanishing theorem. It has a homological dimension 1, so we know if we put the extension groups together and take the direct product, take the sum of them, and then take the tensor algebra with shuffle product and deconcatenation coproduct, it will make, this is a Hopf algebra and it's isomorphic to OU. However, this isomorphic is not canonical, for example. That means it does not work in families. For example, if we compare this with our Hopf algebra, we see, in this case, we have C star shifted by 1, C star tensor C star, and on our side, we have C star tensor C. But there's no canonical isomorphism between these two things. So another explanation is, if you look at this C star 1, it means, for example, this mixed Hodge structure has a C star shifted by 1 value period that is well defined. However, it does not exist. That's why we look at in families. So on the point is fine. Okay. Now we are good for the story at one point. We move on to some generalization and move on to the world of variations of Hodge structures. So how can we generalize our construction? The input is Q, C, and the subspace Q1. We can replace Q by any field K, and C by any dg-algebra over K. And replace Q1 by some K1 subspace in R that we call a Tate line. It is a K vector space satisfying something that Q1 satisfies. Okay, then following the same construction of K, although we didn't really introduce it, we will get a Hopf dg-algebra, and it's graded with an extra grading, so A, R, D. Still, we only give a glance at it. 0 part is K, A1 part is R0 over K1, A2 part is R0 over K1 times R0, and with a single R1. Note that there's no R1 tensor. So the only non-trivial part of D on A2 is, the Hopf algebra structure is basically the same as A, but so the differential is given by this. So R0 over mod K tensor R0 or mapping to R1, that is the differential. So it sends A bar tensor B to dA times D. One can easily see the right hand side is rising R1. So here the dots denotes the extra weight gradient. So the differential does not change this way. Okay, so that's a glance at it. So anyway, we can construct some Hopf algebra. The main application is when R is equal to omega x. Let x be a complex manifold. We consider the dynamic complex of sheaves on X. Then we can construct a graded Hopf dg-algebra A of omega x. And for regular variety with normal crossing divisors, we can use omega log instead. Okay, the theorem is the fundamental Hopf algebra of the category of MHTS is this thing. That is, we take the Hopf algebra with the differential, and we can take H0 with respect to D. And in a more explicit way, we can use all of x to construct A. And then we can start with all of x and then apply our construction to get the Hopf algebra. Then it just means the differential on this thing is 0.
Do you have a base point on x? Is R connected or something? No, augmented, sorry.
No.
No.
No. So in other words, this category is the graded comodule of the right-hand side.
Can you go back one slide to the definition of D, the differential?
Yeah, sure. So for example, this means a function modulo, a function bar tensor, a function goes to D of the first function times the second
You
function.
just have forgotten the formula, I understand what it says, okay.
Is it out now? Thank you. Yes, this one application. Am I going too fast? Anything you want to see?
Well, you can tell us, I mean, what the whole Hopf algebra is. It's not, at least for the point, you've never said that it's just C star tensor a whole bunch of copies of C.
Yes.
I mean, that's what it's saying.
Yeah. Okay. I will introduce that soon. So yes. Here is the last application. So the Kobar complex. If we take the Kobar complex of this Hopf algebra, then it's related to the Galois complex. That is, if we take the total weight M part of this Kobar complex, it is quasi-isomorphic to the weight in Galois complex. So that is, to give a quick review, our Hopf algebra, for now at least, it has 3 applications. It can describe the category of mixed Hodge Tate structures, variations of that, and it can give another model for the Galois complex.
So, is there any use for the higher cohomologies of this complex? You have only H0. Or is this hidden in this Kobar construction?
Yeah, Kobar construction.
No, so the use of the higher cohomologies, is it hidden somewhere in the next theorem?
Yeah.
Yes.
There is none.
There's none?
I can't fully understand what I should expect it would be.
Well, it'll depend on x, right? I mean, if it's a point, it will have no high homology, but I'm pretty sure
That's
x is,
Yeah.
I can construct an x with a higher homology is non-zero. But it's okay, I mean,
Yeah. For the general case, we don't know much about the higher homologies. But I believe we believe that they work they should have some applications. For example, we expect this, or rather the Kobar complex of it, can be the fundamental Hopf algebra of the dg category of complexes of variations. So because H0 is a variation, so we expect that to give a good model for the dg categories.
This is sheaf over x. So
yes.
sheaf H0 something like that is sheaf of variation.
Yes. This is the right hand side is a sheaf. Yes.
Sheaf of category. I mean, if you fix an open set of x, then you can construct such things. Omega x dot is a sheaf on x.
Yes.
So for given open set x, you consider like this way.
Yes.
Then so for an open set, you give a category. Category.
No, not really.
Fundamental
Yes. For open set, we give the category of variations of mixed Hodge structures.
So
we can go together to get the variations over the whole X.
So it is a sheaf of category. So for any open set, you attach one category.
Yes.
So it is C4 category, and it is, this equivalence is equivalence of C4 category.
Yes.
But this, I mean, to come back to what Francis said, I mean, somehow the base point should, I mean, it's a, somehow lurking in the background is an issue of base point.
Yeah, it's,
So,
if X is
But
irregular-
base point is always good base point.
No, that if X has irregularity, then not every unipotent vector bundle is globally trivial.
Right.
So if X is quasi-project, is unirational or something, then you have a canonical Dram-Philo functor by extending to a compactification and taking global sections. But if X has some irregularity, then not every unipotent vector bundle is globally trivial. So there's a fiber functor.
Well, it's a
But if
fiber
R is
function.
augmented, then if R is augmented, then you take
No, but the fiber-
point. So it'd be fine.
Couldn't you have a fiber function to sheaves?
Yeah, you could.
yes.
But we have vector spaces here. I think.
Yeah. No, these are sheaves.
Ah.
This is a sheet, yes. So at each open set, it gives a vector space.
Ah, okay.
Oh, yeah.
So A of omega is a sheaf of Hopf algebras.
But suppose I was
Ah,
really
okay.
interested in variations of mixed Hodge structure over all of X. Do I have to take some sort of R gamma of this thing, or I get a
Sure. You want the
Oh.
variations over? Sorry?
Yeah, I mean, so I'm interested in the set of variations of mixed Hodge structure over a projective variety. So, is that, I mean, how do I get that?
Keep it more complex.
So I guess I get it as a co-module of sheaves
Yes, yes.
on all of X.
Yeah, it's a little bit complicated.
Yes.
That's fine.
That makes sense.
Thanks.
Okay. That's the main applications, and now let me give some detailed instructions. So maybe we can work with the most general case, where so we start with the dg-algebra with a Tate line, and then 0 element and the basis for the Tate line, and we can just construct this Hopf algebra. It won't depend on T. For simplicity, you can assume D is 0, R is R0, and K is Q. That's reduced to the classical case. So, as a vector space, so it is nothing but the tensor algebra, but the first factor is mod out by K of 1.
Question, do you need the K of 1 to be in the kernel of D?
Yes, there are some conditions to call it a Tate line. Yeah, but we didn't put it in the slides. Yes, it has to be something called a Tate line. The conditions that lies in the kernel in D, and we think it should be commutative with the whole R. And it's a K vector space. The lies in they're all invertible. So I mean other than 0, K1 star is invertible. Lies in the center. Okay. Now where are we? So yes. So this is the vector space. Explicitly, it is so it's with 0 part. In some sense, zero part is K, and then you have R mod K1. Tensor R, tensor some power. So that is now we can make some more. So A0 is K, A1 is R mod K mod of the Tate line. This is not another gradient, so maybe put it Poisson shift. R1, R0, R tensor base, yes. And in some sense, way 2 part is R, let's call this R bar. Then this is R bar tensor R. And the next term is R bar tensor R tensor R. And more copies of R's. So this is the space. It's pretty easy. We can consider it as a quotient space of the tensor. Now we introduce the product and the co-products. The product is the Poisson product. So it can be defined recursively by this formula. So let's read it. So x1 to xp, y1 tensor to yq. So first you take out x1 and make the product for the left beams. You can also take out y1 and take the product of the things left. Or you take both x1 and y1, you divide it by t to make it have the correct weight, and tensor by t to take the place, and then you take the product of the left beams. For example, if you think P and Q equals 1, you get x1 tensor y1, y1 tensor x1, and x1 y1 tensor 1, basically. But note that T is not is not in K, so it cannot go through the tensor algebra, the tensor product.
So is this the same
On
formula?
the shuffle product, you've got like one extra term.
Yes.
You got 2 here.
Oh, wait.
No, it's got one extra
No,
term.
just
Just
one.
one extra term.
Oh, never mind. I see.
Three
Yeah,
lines.
it's just that degree term. Okay.
Yeah. It's quite similar to the shuffle product you defined, but I didn't know how to compare these two things, but they should be relative.
I think you just had to insert this degree term
Yes.
to make it come out right.
Yeah. Okay. And
So this is the same formula if you go up to degree 2. It's the same formula as the beginning sheet.
yep. And we have to fix the signs. So a priori we take the positive, and the negative for this term, for this extra term. And if R is graded, we have to take the grading into consideration. But these terms are just the Euro ones for graded algebras. And the coproduct is just the Euro one. You put a bar at any place you can put. In on DR, there's a differential. Now here's the detailed form. Now I'm sorry, there's a typo. So there's no tensor here. So it's dx1, x2, tensor the other things. Or you put the dx1 here and take the differential of the other things. Or rather explicitly, it is, for example, d of x1 tensor x2 tensor x3. We already see how dx1 x1 tensor x2 is dx1 times x2 tensor x3 plus x1 tensor dx2 times x3. Maybe plus minus if there's a degree involved. So that's the differential. Basically, you put two things together and somehow contract them. And the last thing is about the grading. We have two gradients: the cohomological one and the total weight. The total weight takes the number of tensor components into consideration. So the differential D has cohomological degree 1, of course, and the weight of it is 0. Note that such product, such Poisson product and the co-product does not make TR by algebra. So on the tensor algebra, this and this are not compatible. However, if we take the quotient to work on AR, everything works perfectly. So AR is a graded Hopf dg-algebra. And that is the construction for this. Okay. So maybe now we can go back a little bit to review this. So that's why we have this A in A0, A1, A2, and the product, and in the coproduct, this term is crucial here. And we have, for example, that's also why we have this. And the applications are, we have the theorem, we have the theorem for variation of mixed Hodge structures, and we have the theorem to relate this with the domain complex. Any more questions here? No? Yep.
Could you go back to the slide with the quasi-shuffle?
This one?
So that, it's pretty similar to my quasi-shuffle algebra, but
Yeah.
you had to put the degree term there, and then you had to do this thing with the T.
Yes, exactly. I think in your construction, you write it in words and products of them.
Yeah.
In that case, x1, y1 divide t and times t, and x1, y1 is the same word. But in our case, there are two different things.
Right.
Yeah. That's why it deals, they are not compatible on TR. And that's why we need to go to a quotient of it. Yeah, just from the algebraic perspective, that's why.
Is there some intuition for this differential, this B you've got here? It looks like x3, you're not, does x3 need to be closed? Can you have a, it's as if x3 never gets differentiated, so can it be?
I don't think so. Yes, because we have enough time left, I can explain something more. So I'll go to right. Yes. Yeah, for example, I explained, so we want to consider H0 of A omega x d. Right. Let's try why we have this framed object here. So 1 2 pi I squared 2 pi I log z negative v1 negative v2. Well, this is a variation of framed Hodge structure, and let's see how the d works here. So because this maps to, let me write it in this way. So negative v2 or 2 pi. Quotient 2 pi bar. Here bar means modulo 2 pi cube. Tensor 2 pi. And this is negative and plus this one log c bar tensor negative v1. So let's apply d on it. Now it maps to d of negative v2 minus plus d log z times v1. Yes. And that's why d equals 0 implies Griffith's transversality as an example. So because that's how we define v2. And from this example, we can see there's no closed assumption on the last component. Yeah, and this is an example why we want to consider the kernel of D to describe the variation of mixed Hodge structures. Okay. Oh, we have more time. Great.
Question. So is my impression correct that this, when I look at it, is from higher algebraic theory? And this is just the Milnor part of that.
Sorry, I don't quite understand that.
So all these explicit calculations, do they correspond to calculations of Steinbach symbols? Is that the reason why this is state?
What was the question? You say, why does this look like null-decay theory?
Yeah.
Because if you have a unipotent variation of Tate type, everything's coming from df over f. And so it just propagates. So the variation of z by z of 1 is just the invertible functions on x. And so if you've got any variation, you've got all these 1 extensions, and that gives you all these functions, and they generate all this other stuff. The iterated integrals of them generate all the periods.
Well,
These are constants as well.
I mean, so far we don't have, in fact, we were talking about this, we would expect a map from the bar complex on the cycle algebra
Yes.
with two these things, right, which would amount to the Hodge realization. And since the cycle complex is in this state, then that would be the realization.
The cycle complex in the sense of your
Over a point.
Yes, we're expecting such a map, but we were working on it, but it's not quite trivial.
No, it's not quite true.
If there's no question with the things I talked about, I think I do have some time to talk about the. I think I do have time to talk about because I claimed at least, for example, at a point, the mixed Hodge Tate structures are comodules of this Hopf algebra. And the natural question is, given the comodule of this Hopf algebra, how can we recover this object? So I didn't put it in the slides, but since we have time, we can talk about that. No, that's fine. I think it's so let's start with it. So what is so first, what is I can sketch an algorithm, and then I will give a quick example. So the comodule for what is the comodule of our A of C? It means a vector space over C, or graded. It means a graded vector space together with a commodule structure means VC tensor A dot C. Right. Or in other words, a VC tensor VC dual mapping to A of C. Okay. And we know AC is a quotient of TC, the tensor algebra of some copies of C. In fact, it's the direct sum of some C's. So the first step is I claim without a proof here, this map can be lifted here. The lifting is not unique, but there doesn't exist a lifting. That is, we can consider VC as a TC commodule. And after that, we can, but after that, this gives us the period map. So the first step, So the first step is lifting to the tensor algebra. And the second, just one. The second step is to give the period map. Period matrix. But once we know the period matrix, we're following the notation for the period matrix. We think we know the mixed Hodge Tate structure. Okay, now that's the algorithm, but I won't give much details on that. But let me do it in example. So still in this example. So we know it maps to it doesn't work, sorry. Okay. So it maps to negative v2 log 2 pi I phi, that's a 2 pi I plus wait. 6 minutes, okay, I think I can finish. So it means, so we have to choose, now what we have is some basis, C1, C0, C1, and C2, and then we say, for example, C0 tensor C1, due, I claim it will map to negative 1. And C0 tensor C2 due, it will map to the complicated thing, negative v2 log 2 pi I, or tensor 2 pi, another negative sign plus log z tensor v1. Negative 1. And the other easier part is C1 due or C1 tensor C2 due will be log z. So I claim, assuming the commodule structure is given by this, then we will be able to recover this mixed Hodge Tate structure. So this is just an example. I mean, we do have an abstract algorithm for that. But now let's forget about that matrix and see how we can recover it from this. A priori, they are all in R because they rise in a. So the first thing is to lift everything to the tensor algebra. That is, we have to choose a log z, and then choose a v1. And we have to choose a log z and the v2 here to make everything compatible. So I will skip the details, but so the first step is choose them. And now we already have these things. So that's how we can have this decomposition. So now we can rewrite it. So you put negative v1 here, you put log z here, and then we are allowed to skip this term and just put v2 here. And we want to correct the weight, and that's it.
So in the case of weight 3,
yes,
you have the freedom to add a multiple of z to 3.
Yes.
So how would you fix that? In general, not in
yeah, for example, with 3, the input will be like negative v1 log z, and the weight 2 part is a little bit complicated. But the algorithm is you first pick them, and then you will be able to find the parts in weight 2, so weight 1, or in fact negative 2, negative 4, negative 6. So after choosing this, you can choose this to make it compatible with that. And finally, you will be able to choose these things. Then you lift everything into T of C.
But in the last step, there's a freedom to add a zeta 3. Because you could have a non-trivial extension.
Yes, for example.
So where does that data come from?
Yeah. You mean, for example, in two cases, you can add a 2 pi here. Do you mean that?
2 pi squared.
2 pi.
2 pi if you divide it.
Or 2 pi squared divided by 2 pi, yes. Is that what you mean?
No, not really. The analog in this case would be over a number field. So it's only where the constants come. So if you had a constant variation, just the zeta 3 constant family, then where does the data for the period zeta 3 come from?
If you have a constant thing, that means 1 to pi some a here.
Yeah, for example.
Do you mean a in q?
Yeah, for example.
But for a in q, this is the pure Hodge structure.
Yes.
Then for this simple thing, this maps to basically you only have weight 1 things, and it will map to a bar that is equal to 0. So you may either write 1 0 to pi or 1 q to pi for any q. But as a pure Hodge Tate structure, they are equivalent.
It's a common.
Change of base.
Yes, it's just a
Change of
base.
Base part. Changing base or base part.
I see.
So at least as a mixed Hodge Tate structure, they are equivalent, and then in fact they are both pure. So that is great. In this very simple example, I very quickly show how to recover the mixed Hodge Tate structure from the commodity information. So that's my talk, and thank you for your attention.
Is there any questions?
Yeah, so a long time ago, Steve Zook and I proved that the category of, say, mixed Tate, in more general than this, but for example, the category of mixed Tate variations is equivalent to the category of representations of the unipotent pi1, the Hodge representations. Can you recover that here? Looks like it should be Steve Zucker and myself.
I think it can, but we didn't work on it. Thank you for the suggestion. So one of the points of our thing is everything is explicitly expressed in periods. So yeah, that's one of the advantages we have.
Maybe I have a remark. This is this Hopf algebra is isomorphic to the bar complex or Green complex with certain strange multiplication formula.
Yeah, I talked with Professor Tate, so my...
It's true.
It's not question.
Any questions?
Then let's try to speak.